This is the Chapter 8, Unit 8A test review, which encompasses sections 8.1, 8.2, and 8.3. Problem 1 on the review packet asks you to describe the relationship between the values in the table as either direct variation, inverse variation, or neither, and to write an equation to model it, basically, if it is direct or inverse variation. Remember that direct variation is any set of data that follows the equation y equals kx, where k is found by dividing all the y values by their x values, and if they're all the same, then it's direct variation. Inverse variation follows the equation, variation follows the equation y equals k divided by x, which means that k is found by multiplying the x and the y values, and if they're all the same, then it's inverse variation. If neither of those things happen, then it's neither. Alright, so let's start by checking to see if it's inverse variation, because it's the easiest thing to do. Let's multiply all the x and y values and see what we get. We get negative 16, and negative 16, and negative 16. Look, they're inverse variation. I don't even have to check if it's direct variation. If I did y over x, 8 divided by negative 2 is negative 4. Negative 4 divided by 4 is negative 1, and negative 16 divided by 1 is negative 16. You'll see they're not the same, which is why it's not inverse variation. All right, if it's direct variation, then, inverse variation, then negative 16 must also be the value of k. So the equation is going to be negative 16 is equal to x times y. And when we solve that equation back for y, it's going to be negative 16 over x equals y. And this set of data is inverse variation, and the equation that represents it is y equals negative 16 over x. In problem 2, we want to describe how the variables in the given equation are related, assuming k is the constant of variation. In other words, do each of the variables, and the variables are x, y, and z, are they directly or inversely related to k? And that depends on where they are in the fraction. Now, first of all, this is called joint variation because there is more than one variation going on. The x in the numerator, since it's being multiplied by the k, we're going to say that x varies directly as p. Or actually, I probably should have done that the other way. We should have said p varies directly as x. I'll do this, because we normally do it output and then input. And then, since y and z are in the denominator of the fraction containing k, those are both inverse variation. So we're going to say p varies inversely as y and z. And you don't have to make two separate statements if there are two variables with the same variation. So again, p varies directly as x because x is being multiplied by the constant. And p varies inversely as y and z because y and z are being divided into k. In problem 3, it says the momentum m is jointly proportional to mass m and volume v. That means the equation is m is equal to k, little m, little v. The problem is as simple as that. When you say jointly proportional, it's going to be direct variation with k. It's just that it's multiple inputs, and the two inputs are mass and volume. In problem 4, we want to determine if there are any removable discontinuities from the function f of x is equal to x plus 2 over x squared minus x minus 6. A removable discontinuity is a whole. It's called removable because if you do factor cancel, something cancels. So let's factor the denominator. Remember, when we factor a trinomial, we're looking for the two numbers that multiply to give you the last term. I make that look more like multiplication. And add those same two numbers to get the middle coefficient. So what two numbers multiply to give you -6, but when you add them, you get -1. You don't have a lot of choices. It's one of these. Those are the only products that multiply to give you -6. But the only one that adds to give you -1 is that one. So in factored form, it's x plus 2 and x minus 3. Oh, look, I have a common factor in the numerator and denominator, and it cancels. Yes, we have a removable discontinuity. And not only do we have a removable discontinuity, the removable discontinuity is at x equals -2. The way you get it is you take the removable discontinuity and set it equal to 0 and solve for x. In problem 5, we want to find any vertical asymptotes of the graph of f of x equals x minus 5 over x plus 1, x minus 5, x minus 6. Vertical asymptotes, which are vertical lines that the graph gets closer to but never touches, are not removable discontinuities. I want you to notice there is a removable discontinuity. And that removable discontinuity is at x equals 5. Remember, I set x minus 5 equal to 0 and solve for x. So anything else that's in the denominator, and the denominator only, that is not removable is a vertical asymptote. Yes, you can have more than one vertical asymptote because we can get some pretty crazy looking graphs. So the vertical asymptotes are at x equals -1 and at x equals 6. And there are two of them. If you were to look at this graph on your calculator, there would be some line here that the graph doesn't cross, and some line here that the graph doesn't cross. We don't worry about the hole, because the hole, you can't see it on the calculator. You can only see it when you go to the table function, and you'll notice at x equals 5, the y value will say error. Find the domain of this function. Remember, I said finding the domain, which is also the same as what we did when we were finding vertical asymptotes and holes, is the value of x that makes the denominator of the fraction equal to 0. Well, we need to first put this in factored form, both the numerator and denominator. And the reason we have to do both the numerator and denominator is because we have to find out if there are any holes. Okay, so the numerator, when you factor it, the two numbers that multiply to give you 3, but when you add them give you 4, are 3 and 1. +3 and +1. The denominator was a special type of factor. It was called a difference of two squares. It factored into x plus 3, x minus 3. So what I want you to notice is that there is a hole at x equals -3, so it's a restriction on the domain. And there is a vertical asymptote at x equals +3. Remember that only the denominator is going to give you vertical asymptotes, not the numerator. So if I want to know what the domain is, the domain is x cannot equal -3 or +3. The domain, which is the same as finding the holes in vertical asymptotes, it's written a little bit different. So we say that the domain is x cannot equal -3 and +3. In problem 7, we want to describe the conditions that will produce a rational function with a graph that has vertical asymptotes. You're going to get a graph with vertical asymptotes if, let me say vertical asymptotes, if you have a function with factors with x in the denominator of a fractional function that cannot be canceled with a factor in the numerator. There's the wording. I don't know if it's the correct wording, but, you know, it tells the story. You're going to have vertical asymptotes in a function. If you have a function with factors that have an x in it, so, you know, something like x plus 1, x minus 2, in the denominator of a fractional function that cannot be canceled with a factor in the numerator. In other words, if you have a function like y is equal to x plus 3 over x minus 2, x minus 1, you're going to have vertical asymptotes because you have factors in the denominator and they cannot be canceled with something in the numerator. Now let's do this again with wholes. If you have a function with factors with x in the denominator of a fractional function, that can be canceled with a factor in the numerator. Move that up. So in other words, if you have a function like x plus 2 over x plus 2, x minus 3, because the x plus 2's can be canceled, you will have a whole. Number 8 says, if you evaluate a function at a point and you get an error, then what does that tell you about the function, about the rational function? Anytime you plug a number into a function and you get an error message, it means you are either going to have a whole or a vertical asymptote. You're not going to know which one it is unless you actually know what the function is, so you can determine if it's a whole or vertical asymptote. Or if you graph it, if the graph doesn't look like it has an asymptote at a point, and you go to the table and see that it says error at a point, then that's a whole rather than a vertical asymptote where you kind of see the graph getting closer and closer to something, but it doesn't really pass through it. For problems 9 and 10, we're just going to write an equation that models the variation. Notice it does not ask me to solve it. It just asks me to write the equation that models the variation. So in number 9, it says if y varies inversely with x, let 10 equal, or let x equal 10 when y equals 50. So the first thing is the keyword inversely, which means it's the equation y equals k over x. Because k is equal to x times y, we can find the constant of proportion of variation by multiplying x and y, and 10 times 50 is 500. So the equation is y equals 500 over x. In problem 10, it says if z varies jointly as x and z, let z equal 20 when x is equal to 8 and y is equal to 6. So the equation is going to be z equals k x. Oops. Whoa, there was something wrong with this. I made a mistake. That says y in the problem. Haha. All right. If z varies jointly as x and y, let z equal 20 when x equals 8 and y equals 6. So the equation is going to be z equals k x y. In order to find k, I'm going to plug these numbers they gave me into the equation, and I'm going to solve for k. So 8 times 6 is 48. So k is going to be 20 over 48. Let's see, that I don't have a calculator. So they're both even, so I'm going to get 10 over 24, which reduces to 5 over 12. That must be as far as it reduces. So the equation must be z is equal to 5 over 12 xy. Number 11 says the amount of gas G you purchase varies directly with the budgeted money M and inversely with the price of gas P. Write a formula. All right, that's going to mean G is equal to K. Now let's go back through the problem. It says it varies directly with the budgeted money M. So there's my direct variation. And inversely with the price of gas P, which means it's over P. So the equation must be G is equal to Km over P. In problem number 12, it says we want to mix a 10% orange juice drink with 100% pure orange juice to make a 40% orange juice drink. The function y equals 3 times 1 plus x times 0.05 divided by 3 plus x gives the concentration y of orange juice in the drink after you add x gallons of the 5% drink to 3 gallons of pure juice. How much of the 10% drink must you add to get a drink that is 40% juice? In other words, when will this equation equal 0.40? The best way to do the problem is the same way we did it in section 8.3. Put this in, I don't know, y1 or y2 equals. I'd probably put this one in y1 equals and put this into y2 equals. Remember, when you plug this equation into y1 equals, you need to add a second set of parentheses around both the numerator and the denominator. If you don't, you will not get the correct graph. After you graph it, the problem that was in the lecture notes in the book, you had to change the window to find the answer because the answer was a huge answer for x. This one you don't have to change the window. If you use the second trace 5, enter, 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 it will tell you that the answer is approximately 5.143. Well, we're going to say that x must be approximately 5. We've got to add about 5 gallons of the 10% drink to make a 40% drink. The last problem is the performance assessment task. The one here is very similar to the one on the test. You're given the equation y equals x minus 3 over x squared minus 7x plus 12, and you want to first identify the domain of the function. Well, to find the domain, you need to factor the denominator, the two numbers that multiply to give you 12, but when you add them, give you negative 7, or negative 3 and negative 4. And then you would say that they cannot equal 0, so x cannot equal 3 and cannot equal 4, and that would be the domain, because those are the two numbers that both make the denominator equal to 0, and therefore you'd have an undefined function. In part B, they want you to identify the equation of any vertical asymptotes and any holes. Well, once you factored it, this is what we have. Because I can cancel those, that must be a hole, and the hole is at x equals 3. Anything else left in the denominator that can't be crossed off is going to be a vertical asymptote, and there is going to be a vertical asymptote at x equals 4. There is no part C on here, which is kind of interesting, so I guess we'll just skip down to part D, which says graph the function. So I would say, in order to get a decent graph, you know two things are happening. One of them is that at 1, 2, 3, 4, there is a line that the graph does not cross. And the other thing, you know that at x equals 3, there's actually a hole in the graph. So if you want to use your calculator to help you graph this, that's fine. But I would start by putting any asymptotes on the page. So remember, if you put this into your calculator, make sure you put the numerator in parentheses. And I would go back and use the original denominator and put it in parentheses. And you'll see that the graph looks like this, which means that the whole is going to be somewhere around here. Hint, hint, the problem on the test is going to give you a function that's more in this format. This isn't the exact problem, but it's close. And they're going to ask you for one additional piece of information, which is the constant of variation. The constant of variation is just that number. It's your A in the equation that tells you the transformations on your parent function. And that is the Chapter 8, Unit 8A exam review.